Hi guys, I hope you're doing well. This is lesson 4 for our final unit, so we've only got one more lesson after this. But this lesson, it's going to look like a departure from the normal distribution, but really it's definitely in keeping with some of the theory behind the normal distribution. It's what's called confidence intervals. And you've probably read online or in a newspaper, whenever they give opinion polls, like during an election and they're trying to predict who they think's going to win an election, they'll often poll a whole bunch of people, but they'll give these stats with a certain amount of confidence, and they'll often say things like this. They'll say these results are accurate to within plus or minus a certain percentage, and then often they'll give this, which is 19 times out of 20. And we're going to talk about what that means. But if you think of 19 times out of 20, really that equates to about 95%, or exactly 95%. So we call this a 95% confidence interval. And it's really tough to get to higher than that. You can up to about 99. But it's saying that 19 times out of 20, if you were to repeat this study, you would find the exact same or results within a certain percentage. And let's look at an example here. It says a survey recently published by XYZ Consultants found that 73% of Canadians regularly watch ice hockey games on television. And the survey interviewed a representative sample of 1,200 Canadian adults and has a margin of error, so that's a terminology we're going to use, of plus or minus 3 percentage points 19 times out of 20, i.e., like we were saying, 95% of the time. What they're saying is that 73% is the best estimate of our percentage of ice hockey viewers in the whole population, and the true value is to lie within a certain percentage of that, and that's where we get this lower limit and upper limit. So we know that it's plus or minus 3% of that number. In other words, we're going down 3 from 73, so 70%, and up 3 from 73, so 76%. And we're confident at a level of 95%. So strictly speaking, we can infer that if we were to do this 100 times, 95 times out of 100 in the sampling procedure, we would produce values between 70 and 76. And so this kind of idea is used in medical studies, basically anytime you're sampling anything. So in sociology and science, you're going to have this level of confidence. And I just want to briefly talk about the theory behind this. And I just also want to note that this is just an introduction. And if you go on in stats, which most of you will have to take some stats courses, you're definitely going to explore this in greater depth. So how this ties to the normal distribution. You remember when we started looking at the normal distribution and we learned this rule, the 68, 95, 99.7 rule. Basically, if a population is normally distributed, which a lot of times you're going to find certain things that can fit the normal distribution, we know that 95% of all observations are within 2 standard deviations of the mean. Looked at another way, if you know your population fits the normal, for example, if I looked at all of the students of the school, and I just randomly picked students out of the population, I know that, for example, their height of a student would fit within 2 standard deviations. I would have 95% out of 100 of those students would fit that. So if I picked one, there's a 95% chance that I'm going to have a student that falls within a certain range. And that's what this idea means, is that you have this 95% of the time, the mean will be within 2 standard deviations of that observation. And that's where you get this confidence interval. And so when you take a sample and calculate the mean of the sample, and we call that the mean of the sample X bar, like we were doing before, you're really finding an estimate of the population mean. And the population mean, you might remember, is called mu. So if you follow proper sampling techniques, which we talked about earlier in the course, your estimate is more likely to be representative of the population. However, It's always possible that your sample will include extreme members of the population, and thus your sample will not be representative of the population, and you would be the 5 out of the 100, the opposite of the 95, where that's the case. And sometimes that happens. This is why most studies give the results in terms of a confidence interval. And so what a confidence interval demonstrates is the range of values that the population mean is likely to have, and then also the probability that the mean will fall within the range of those values. And so we're going to look at some of the calculations that come with this. Excuse me. So let's look at this example here. Let's say our data management class has had an average of 81%, plus or minus 6%, 19 out of the last 20 years. If we break this down, it means that the average has been between 6 below and above 81, so 75 and 87, 19 out of the 20 last years. So the plus or minus part is what's called the margin of error, or E. The range is the confidence interval from the lower to the upper limit, and the 19 out of the 20 indicates the confidence levels. And that's happens when we have 19 over 20. So this is where in a university course you would have a stat sheet, and on your stat sheet you would have a whole bunch of formulas, and this is where a bunch of formulas come into play. So I just want to fix this. This should be square root there. So one thing is you can have different confidence levels, and these all come from the Z-score table. And so sometimes you only have a confidence level of 90%. From the Z-score table, you get this value of 1.645. And 95%, which is almost a Z-score value of 2, but exactly is 1.96. And then you can get all the way up to 99%. And these are the ones that are often used in medical studies, because they want to have the most confidence in their results. They don't want to have any variation, because often that's going to be something that could lead to fatal results. So if we take an example here, and we're going to use this formula here for E. Remember, E is the margin of error. And if you go on in stats, you'll talk about the derivation of this formula. But for now, this is what we're going to use. So basically we have the Z value, which is the Z-score confidence level, and that has to be given within the question. And then we have this P, which is the probability of success within the example. E is our margin of error, which we talked about, and N has to do with the sample size. And just like before when we were doing sampling, the greater the sample size, the more confident you are generally in your results. So if we looked at this specific example, it says data management classes have been sampled for the last 10 years. The course average has been 76.5%. So this is my P. So P equals, and I'm going to change it to a decimal, 0.765. That's my probability of success. And it says determine the margin of error for this survey at a confidence level of 90%. So the other things we need here is my Z, which is the 90%. And so I go to this one here and I say, okay, that's 1.645. The other thing we need is N. And because we're looking for E, that's the thing we are looking for. And N in this case is going to be 10, because this is 10 years that it's been sampled. So if we plug all of this in, and in stats, there's often a lot of just subbing values into formulas, but you need to know which formulas to use. And so and so you can work this out, and I would try to do that because it is a bit tricky, especially with the root. But it comes out to approximately, so my E is approximately 0.222. And so this is equivalent to 22.2%. And so my margin of error is 22.2. So that means I'm going to go above and below 22.2%. So the next part's going to relate to that. So it says determine the confidence interval for this survey at a confidence level of 90%. So that's what we were working with. So this is where I can figure out my lower limit and upper limit. So my average X bar is given, which is nice. And then my E, we just calculated above, is 0.222. So my lower limit for this confidence interval takes those two things. And so if you work that out, that becomes 0.543 or 54.3%. And then similarly with my upper limit, I'm just going to sub it in directly. And I get 98.5 or 0.985 if I'm working in decimals. So my confidence interval is from, and I'll convert back to percent, 43 or 54.3% to 98.5%, like that. So pretty high range of values. And again, it's mainly because our N value was quite small, so the number of samples is pretty small. And next one says the second survey was found prior to this study, and the study had an average of 82% with a sample error of plus or minus 2%, and had a confidence level of 95. And they're asking us how many years were sampled. So let's write down what we know. So we've got study average of 0.82, so that's my P. Error, E, is 2. And my Z-score based on 95% is coming from here, so that's 1.960. And what we're looking for is N. So what we can do is take that formula, so E equals Z square root and so on. And I need to sub in or rearrange to solve for N. So I'm going to sub everything in. And so a little bit of algebra to figure out. So first thing I can do is divide both sides by 1.96. So I move that over because I'm trying to get an N. And I can also square at everything at the same time to get rid of the square root. So now, if I move N to the other side, I'm moving N up and the other part down with the squared. So I have 0.82 divided by all of that there. And so that comes out to 0.1417. And the reason we have a decimal is because we've converted our percents into decimals. So what we need to do is times this by 100. And again, it's because of this 0.82 here. And so this is going to be 14.17 or 14 years approximately. And so it tells us the number of times that were sampled and works out that way. Okay, so some things to consider with confidence intervals, and again, this is just an introduction. Basically, the smaller the margin of error, the more accurate the measurement you're going to have, which makes sense. If your plus or minus is a small number, you're going to have more accuracy in terms of your results. And so if you consider those opinion polls about people voting, they often try to have them within 2 to 3%. So they'll keep sampling until they know they have a confidence level of 95% with a margin of error very small. So 2 to 3% generally is acceptable. And the higher the confidence level, the more likely the result will fall within the given range or confidence interval. And often, as I said, researchers will increase sample size in order to reduce the amount of error. So one study is often insufficient, and so often they'll do these studies multiple times. And again, there's more formulas that come with this, but you can start to predict the mean and the standard deviations based on what you have. And we get these different formulas here. So we talked about these values, so I'm not going to write them out again, but mu is our population mean, standard deviation, and then what we had here with margin of error and z-score and standard deviation. So you can relate these to each other. So I think it's best if we just try an example where you see them. So it says every week a mechanic checks the tires on 10 randomly selected cars. For the last 8 weeks, the average lifespan of the tires has been the following. And then it says results from previous years indicate that the tires have lifetimes that are normally distributed with a standard deviation of 4,800. So this fits in with normal distribution because often we talked about this with lights, but the lifetime of products, basically they have a lifespan where they get worn out, and that fits often into a normal distribution. So the question says calculate the sample mean and the sample standard deviation. So if I want to do the sample mean, all I'm going to do is sum up all of these numbers, so all of my averages, and divide them by n. So if I do that, I'm just going to write out a couple just so you see. Dot, 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 and then divided by the total number, and I believe there's 8. So if you do that, and I'll give you the answer here. So if you punch them all in, you get a mean of 56,000, approximately 33.875 kilometers. And standard deviation is a bit easier. So this is this formula here. We take the given standard deviation and we divide by the square root of the number. And so given standard deviation is 4,800. We have 8 in our sample. So if we punch that in, get approximately 1,697.06. So that gives us things that we can work with in terms of calculating the confidence interval. And so the confidence interval here is going to be based on the margin of error. And so the margin of error we can use from here. So we're going to take the stuff that we just calculated. And so my margin of error for 99% confidence interval, so Z in this case is going to be, if we go back up, that's from here. So that's 2.576. And so E is 2.576 times my standard deviation, which I've got above. And we get a margin of error of approximately 4,300, 71.62. And so now I can get my lower limit and upper limit. So my lower limit takes my mean minus E. So my mean here is 56,000 that we calculated, minus the margin of error. So if we punch that in, oops, 52,000. And then my upper limit, similar, only adding them. And we get, let me see here, 60,000 actually. Okay, So there's a few questions to try out here from the textbook. Again, this is a bit tricky, but keep these formulas in front of you so these